Hi guys, today's job is to make another cylinder rod, another piston similar to this. This is made out of aluminium. It has some kind of hard coating. I think that's some kind of ceramic coating, but we will make it of regular chrome plated rod and cast iron piston. The tricky part is drilling these two holes. These are 20 millimeters in diameter holes, and they are 500 millimeters long. The piston has the total length like 477 millimeters. And one hole intersects with this hole, so the oil is pushed in here to push the piston back, and the other oil port comes out here and to push the piston that way. So we need to make a new one because this is all scratched up, it's all dinged. We will need to make a drill. Uh, Basically, we'll braze a high-speed steel twist drill to a shank, and we will drill this part. First the through hole, after that the shorter hole. And that's it. Let's see how it goes.
And I just use an edge finder to find the center of the rod, and I use a center drill to make two dots for the correct distance between the holes. And that's it in this operation. This is a 500 millimeter forged chuck, and I remove it to put a smaller chuck, and I just weighed it for fun to see how much it weighs, and it's 82 kilograms. A pretty heavy chuck, and for Imperial guys is like 180 pounds. This is how the drill turned out after brazing. We start indicating in 35 millimeters total indicator runout, that is 17.5 millimeters per radius offset. After that we will remove the tailstock and drill with the 20 millimeters couple of inches so that we have a pilot hole. After that we will use the carriage and drill the whole part out. I will start with the standard drill so that even if we had a little bit of run out, to remove the run out as much as possible before the pilot hole. I drill a 8 millimeters pilot hole, and after that I go with a 20 millimeters shorter drill, and after that we will go with a 20 millimeters the long drill, the 500 millimeters shop made drill. I had a little wobble, so I decided to make a bigger centering drill. Yes, I know the center drilling is not the best drill before actually drilling, but I needed the centering drill so that I can put a live center while I indicated the part in. So this is what we need to run with. Do a 20 millimeter drill, just finning it by hand, and it worked great. We start by cutting a little bit of air because we have drilled with the 20 millimeter short drill like 80 millimeters in the part. Now we're starting to make chips. The speed that I was using the drill at is 200 RPM and the feed rate of 0.05 millimeters per revolution. That's like 2/1000 of an inch. And if I saw that it worked fine, I pump it a little up. It's like 240 RPMs with a feed rate of 0.06 millimeters per revolution. That is like 2.5 per revolution. But made a little bit of squeaking noise, so I reduced it to 0.05 millimeters feed per revolution. Because I know the faster you feed, the more likely you are the drill wandering all over the place. And for such a skinny and long drill, I didn't want that my hole ended up in the wrong exit or drilling out of side of the part or something crazy like that. I'm not a hydraulic expert, I don't do hydraulic stuff, but this is one example that what I do. I make all kinds of crazy stuff that other shop basically just refused making, and this is one of the great example. Hydraulic shops will not mess with this kind of cylinders, better said cylinder rods. First hole is ready, and we will see the light on the end of the tunnel, so we have managed to drill it out. Now it's the second hole. Let's see how this goes. So we are finished with the second hole, and this is not true. This is ends before the piston, and we need to drill a radial hole to intersect with this hole so the oil can flow before the piston. One needs to go after the piston and one oil hole before the piston. A quick presentation to this monster long skinny drill that I made. Pretty fun. This chucky is too short for this lathe. I fighted it all along, indicating the part in. I would hit my hands on a chip guard, I would hit my hands on the lathe. So it's time for a quick side project to make a longer chucky for this Weiler A50 lathe. And here I am at the Pinacho lathe with the Fagor controller, and I just determine some numbers for the contour, how I want the chucky to look, and make a quick simulation, and let's see how it goes. The chucky is made out of 4140 for Imperial guys or 42 chromolybden 4 from European guys. It has a 30 HRC hardness, but I will sand it after this to make it like 40 or 45 HRC for better toughness. And I made in the past chuckies with 40 to 45 HRC with this steel, and they didn't broke, and has no wear pattern. So this is what we do again on this chucky. And this is up to, I remove just a little bit of the diameter and make a big radius on the end so it has a nice feel to it. Making the square using the side of the roughing and mill so that it leaves a radius where it intersects with the cylindrical part. I made an offset, I measured, and here we go. All in one pass from almost 80 millimeters to 40 millimeters square, because this is what the chuck has. Okay, so this is how the chucky looks. It clears all the parts of the lathe. I'm pretty happy with it. I'm sad because after the chucky I measured the spindle bore. Basically I wanted to put the cylinder rod in the spindle bore to make the threads for the piston, and the Weiler lathe has a 69 millimeter spindle bore. I measured it in the past and I didn't know that is a 70 millimeter spindle bore, and I thought that is like a little bit oversized, so you can actually put a 70 millimeter round stock in the headstock, but no, it's a 69 millimeter spindle bore, so a little bit disappointed. This is how the threads turned out great, and the diameter to register the piston turned out great. I made a quick chicken sketch so I know what I need to make on the other lathe. We make internal groove for the o-ring and the sliding feet for the register and the threads. When it's possible, when I machine cast iron, I put a rag so the fine metal dust doesn't go in the ways, so I protect my machine as much as I can. Make a drilling with a U-drill and start the program. Here we make a quick internal contour so that we can machine the interior diameters that I made on the sketch and the minor diameter for the threads. On a final pass, I use coolant because the part heated up. This is how much cast iron I catched just with the rag. Testing out the threads, and it turned out great. I flipped the piston, machine it to length and semi-roughing diameter. Now we permanently assemble the piston to the cylinder rod. We put the O-ring in, put some Loctite, and we squeeze it as hard as we can. On the back side of the piston I made 2 holes so I'll be able to put a spanner and tighten it as hard as I can. Be prepared for disaster. 2, 1, and boom! What happened? Guess what happened? My Chinesium high quality C-clamp just braked. It fell apart basically. But it was a quick fix. I drilled an M8 hole and put a bolt through the hole, and it was a quick fix. But we are not finished for today. We have more problems. Focus, focus. Did you see that? Did you see? My column is not tight, so the 4 bolts that pivotate the column are not tight. And I tightened it down and we continue working. A lot happened today, and not in a good way. Fixing a grab screw with a little bit of Loctite and tighten it down in a hole, and that's it. We are back at the Pinaccio lathe to make the grooves for the piston, and we make the first contour. And see that we have a lot of problems, lot of vibration while machining the contour. This is a 1.5 millimeter parting blade. This is a 3 millimeter parting blade. This is a 4 millimeter parting blade. I tried all my parting blades and nothing works. It has too much vibration and it's not good. And we are back to a conventional lathe, SN 502, Romanian made lathe. After we machined the grooves, we need to align back the piston rod with a 20 millimeters drilled hole so we can put the 2 M16 millimeters for holding the cap on the cylinder rod. So although I don't have 20 millimeters pins, but I used the drill and put a little bit of paper so that the drill don't fall in the holes. These are the 2 holes that we are trying to replicate now. My setup is a little bit better because I put a CNC vise sideways so it holds a little bit better, and I put 2 seam clamps because I had some soft jaws. Basically, I had between the jaws and the cylinder rod an aluminum piece of sheet, and I have drilled out, and now we tap it with the M16 hole, and turned out great. To drill the cross hole, I go to another mill and use the same two 20 millimeters drills, so I can make the hole perpendicular to those two holes. And I drill it out with a 20 millimeter carbide end mill because I didn't turn down the chrome enough.
And here is the final part. It turned out great, doesn't have any dings from falling down in my chip tray. I verified it, so we are good to go. The small mistake that I made, I didn't turn down enough the chrome, and I used a carbide 20 millimeter end mill to drill the hole. I wanted not to put it back in the lathe and machine after the hole, so we can use a high-speed CL3 there. And that's it. This is how it looks. It looks great. It's ready to be assembled. Bye.